Last time we talked about the binomial coefficients. These are n choose k, which is the number of k subsets of an n set. And for example, here I have 3 different objects, so I could think about the number 3 choose 2, which is how many different ways can I choose 2 of the bugs? Well, I could choose these 2, or these 2, so there are 3 ways to do it. Now, we could think about these as k combinations without repetition. That's one way to think of this set, which suggests that maybe we should also talk about what's called a multiset, which is written n choose k with double brackets. So this is the number of k multi-subsets of an n set. And what this means is that we're allowed to choose multiple things. So a good way to think about this is that we have a store with lots and lots of the same type of item. And so we can always choose and then put it back. So let's think about what happens in the same example if we do 3 multi-choose 2. What are my possible options? Well, keep in mind that I think of having this infinite string of things that I can sort of always pick back from. So if I'm choosing 2, I could take 2 of the yellow butterflies. So I could take, we're going to pretend the orange and yellow are the same. I could take 2 of those. I could take 2 spiders. I could take 2 ladybugs. Or I could do all the things that I could do before. So that was, if we generate these guys a little systematically, these different combinations. So these are all the different ways that I could choose if I'm allowed, in addition to doing these 3 normal options down here, which are the set options, I'm allowed to choose with repetitions, and I get the answer 6. Now you might recall from last time that we got the answer 6 in another context, which was 6 was 4 choose 2. And what's the connection? And there is actually a connection between these multinomial coefficients and these binomial coefficients, or multiset coefficients. So that's what we want to look at, is how can we understand this number and get a formula much the same way we got this formula, and this is maybe the fact that they're both equal to 6 in this example is maybe suggestive. So let's see what that's exactly suggestive of. Here we'll put down the theorem. If you have n objects and you're allowed to choose k with repetitions, so think of this as you're going to Blue Star Donuts. They have n different types of donuts, and you want to make a box of k donuts. It doesn't matter if you want more donuts and they have different types. You can still get lots and lots of your favorite blueberry bourbon, for example. And in fact, the number that you can get is n plus k minus 1 choose k. So we want to see why this comes up, and this is an argument that's often called, in combinatorics, some things have names, this is called stars and bars. That's supposed to be an ampersand. So here's our proof. Suppose we have all of these different types of things, and in fact, let's give us another type of bagel. We'll have the dinosaur flavor bagel. All right, so now we've got all of our elements here. What we're going to do is we're going to say, okay, well, suppose you're actually going to a store, and maybe you're going to the donut shop. These are going to be put with bars in between them. So however many items I have, however many different bagels, I need 1 fewer bars. So I need n minus 1 bars between the objects of the n set. And now what I think of is I've got money, and maybe my money is the stars. So I've got all of this money, 1 star per bagel or per donut or whatever we're buying. And suppose I want 2 of these butterflies. I don't like spiders. I'll take, you know what, I'm going to take like 3 ladybugs. So we'll spread that out, and a dinosaur would be nice to have. So that's what I'm going to choose with my stars. So how many choices, how many stars do I get? Well, that's how many I'm choosing. So I have K stars to represent choices. And now what do? Well, I'm just making up a word that is stars and bars. So how many letters do I have in my word? Well, I have K stars and I have N minus 1 bars. So I get N minus 1 plus K letters that I'm going to put into positions. And now, if you think about how many different ways can I arrange this word, well, what do I get to choose? I can either choose where to put the stars or I can choose where to put the bars. And it doesn't matter which I choose. So we'll put K down here, but if I put N minus 1, that would work too. So this is the formula, because the N minus 1 bars between all the things that I'm choosing. So then if I wanted to choose, for example, star, 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 bar, star, bar, bar, star, star, this would tell me I want 3 of these butterflies, I want 1 spider, I don't want any ladybugs, and I want 2 dinosaurs. So this is how we can count this. And now if we look back at our example that we did before, we saw that, okay, under this paradigm, if we have 3 choose 2, what does that equal to? Well, that's equal to 3 minus 1 plus K choose K, which is, of course, 4 choose 2, and so 6 was in fact equal to 6, and that's how they're the same 6. So this is your classic stars and bars argument. When you're choosing with repetition, the thing from which you're choosing, the number of bagel types that you have, that you put in bars between them. So you're going to get 1 fewer bar. And now the things that you're choosing, just think of these stars as your money. That's how many you get to pick. And so we just line up our stars and our bars, think of all the ways to do it, so it's just equal to a binomial coefficient.